Let's get started. Pulling right to. Okay. Today's lecture might be a little bit more weird, maybe than normal, just because of the topics are also a bit weird. So we'll probably discuss stuff a little bit more because a few of these things, also as we get towards the end of the class, this is now like stuff that's currently in discussion, kind of in the community and what to do about these things. So welcoming, of course, like maybe more questions than normal or whatever. I tried making these slides. They're probably way too long, so maybe we'll cover half of this today. We'll see how it goes. Um, and all right, so that as an example for how this will start out, we'll cover a couple of different topics. First question for today, though. All right, is this a robot? Thoughts? So Wi-Fi makes something a robot. Autonomously without supervision. Okay. Define autonomously and without supervision a bit more. Just like I just don't look at it. Okay. So a toaster would also fit that description, I think. Okay, so is a toaster a robot? Yeah. Okay. I like that you're sticking with this. This perfect. It's great. Yeah. Is there a timer? It's not a timer. There's kind of like a heat adjusted switch on a toaster. All right. What do you think? Hmm. No. Have you never been camping and had one of those toaster things that's sort of like a disc and then like two arms on it and then you like lean your bread up on that and it toasts over the fire? So it's no? Okay, don't count that version. Okay. Other thoughts? I'm like purposely being tricky here. There's not always a great definition for this, but you're given reasons. So far we've got two for this is a robot. How many people think this isn't a robot? Some definition. No? Everyone thinks a dishwasher is a robot? Hmm? I don't know, maybe I should have picked an older dishwasher or something like that. But it gets down to this definition. Yeah, go ahead. Yeah. So there's a little. So I think you're getting to the point like, well, now you're starting to think about it's like planning ability. Like, does it do anything closed loop, like reactability? So it depends on how new your dishwasher is. Some of the new ones at least have a sensor in the water filtration system to figure out, okay, like what is the particulate matter in the water right now? So if it's still like full of a bunch of gunk, it means there's still more to clean and it'll actually react. I don't know as many of the details, but it might also change the temperature for the water. But there are at least some versions that do have a sensor. I think anything that's like newer than 10, 15 years old will have one. Okay. So then things that react or have a sensor or also has to react to use that sensor. Okay. Oh, it's up you. Hmm. I mean, some of these were also defined in like doing stuff a human does. Um, a lot of robots are used in space. It's not exactly the popular location for people to do work. Definitely outnumbered out there. So that's sort of maybe an adjustment in that definition. See. Okay, good. We're at least starting to question whether or not we think any robots exist in the world, depending on some definitions, or whether or not everything is a robot, which is good. That's kind of part of what we're trying to figure out for today, amongst other things. So this is, yeah, you might want to, in this process, start to think about some of the questions related to this. So beginning, like sort of what capabilities are desired for these robots and or models, and maybe usually we always talk in this kind of stuff on the right a lot in the class. And today we're going to try and connect these two together for like, what is a robot? We're talking about its capabilities and generalization. Sometimes it's like reactive nature, what it's able to control, what sensors it actually has. And this is all helpful because, all right, we got to a few of these questions. So kind of anything a person does. But now let's expand on this. So what do you want robots to do? I'm assuming, you're in this class because you're excited about eventually making some automated system. What do you want it to do? So you probably want it to do like your repetitive tasks for you. Okay. You're not just like thinking of repetitive tasks for it to be able to accomplish. Yeah, I mean, that even kind of corresponds with like the reasons computers were made. That's sort of the beginning part is like, okay, is there a system to make that can, do multiplication a couple of thousand times? At least it could be, you can write a little bit faster than people can. All right. Uh, do we just want repetitive tasks? We're just really tired of those. Is there anything else that we would like to see the robots be able to do? Dangerous tasks. So you want to give me a little bit more to that? So it's like you're not thinking of battle bots, probably, if you remember that one. Uh, hmm Hopefully not too many rescue things are too dangerous, but those are related. Yeah, because I give space as a nice example, although it's, no, it's still pretty dangerous as it seems. All right, any other ideas? These are pretty broad. hmm hmm Yeah, there's this whole classification group, uh, surgery. Those are like interesting questions too, because a lot of those are some of the people that do these are extremely highly trained. There's not very many of them, even though there's tons and tons of people that probably need surgery. So it becomes a question of, okay, maybe at least in terms of motivations, is there an area where there's literally like not enough people to support the large population? Things like that. Especially as we like, I don't know, as a group, we've got better healthcare, people live longer, but it also, as you live longer, you tend to need more maintenance. You can trust me on that one, even though I'm not too much older. Uh, sort of a process. Okay, this is good. This is already starting to figure out like we don't, well, I mean, dishwashers are actually pretty great, for the most part, but we're trying to get much further along this actual like things that robots can do, way beyond, what dishwashers are capable of, because it can only actuate a few things. Like it's got a couple of water spouts that it can actually change about its design. Okay. But the conversation of getting into is start to talk about like what we want these agents to do and start to think about the levels of autonomy they have. So some of you may be familiar where like in the community for robotics, at least for self-driving cars, there's been a pretty good description of what they think of as like these are the levels of autonomy. It's even used on like some cars when they're trying to sell you a car. It's like it reaches this level of autonomy, and there's like a pretty good definition for what that should be. And there's even some other cases for those that might be familiar, although the text is pretty small. There's a lot of smart operated buildings these days. Well, not as much as I'd like there to be, but I'm working on that, and so are many other people. But there's levels of autonomy there. Like, can it control the thermostats automatically? Can it adjust energy controls in the building? And there is already a good level of like descriptions of the different levels of autonomy in those stages. But this is all about figuring out basically how to define this process. And then at some point, we can like put, a marker somewhere for what we understand full autonomy is. Especially as we're making more and more large models and we do more and more experiments in those data sets and on hardware. Are we all pushing towards some level of autonomy? I sure hope so. This is where a part that will probably come up in the community recently, and we'll chat a bit about today, sort of like, okay, what does a level of autonomy mean for a humanoid robot? Is it just like packs the dishwasher? Is that like the level of autonomy that we're going to be talking about? Will it figure out how to do those human things, like being at a camping spot and being able to toast on that like metal flap thing as from before? There isn't a lot of work done on this kind of description for these types of autonomy, like just yet. This sort of seems like emerging in the community lately. There is some work for like HRI, and actually a lot of the way autonomy is often defined is, okay, how much does the client, the user, or the person collecting data have to intervene on this process? How frequently, by what amount, by what cognitive load? And then the system is kind of like taking a lot of this work for them. Even here for self-driving cars, it's like, does the person have to occasionally end up correcting the car? Does it drive almost unlimitedly on certain kinds of roads without any issues? And there's just like offloading like chunks of this process. So we'll talk about it a bit more today because it's kind of like connected to basically autonomy and what's coming up in the community called agentic models, which is just, okay, how much of the entire process can be offloaded onto some autonomous system. In our cases, it's more often a physical autonomous system, but this kind of has been a question for a while, and there's a couple of ways to interpret this. So one of these is to start to think about how agents are modeled and to start thinking about the interface that they construct. So, all right, how many are familiar with some of these? Maybe at least hopefully everyone's familiar with the one in the middle. It's from previous slides. Hopefully we're familiar with that one. The one on the left is kind of the typical diagram that's used for robotics. And it's a bit interesting too, because in this case, like this part kind of looks like the RL paradigm in there, if you can read that well in the center. But now it also has these other components for actuators and sensors. So in the robotics like mindset, the idea that something has to physically make something move and something has to actually sense what is going on in the world must be part of the system. It's not just all lumped into one. And this is kind of special because in this case, because of this separation, it's caused for basically, some extra areas of work that happen inside of the robotics community. But it has to deal additionally with the way some of the algorithms are constructed. And then even on this perspective here, for some people that might be familiar with more behavioral sciences, there's even some similar notions across these models too, where some of the text is a little bit blurry, but in the brain, there's an internal state of what's actually going on in the world. And then there's the external state of how the environment actually works. And there's still a model of of sensors, sensations, and actions here. And then trying to make like a seemingly connected model from all of these. Here, all these frameworks are always kind of motivated by a particular problem space. So an RL also got a lot of its information from being able to do like a biological motivation. Robotics tends to like go around a lot of that biological motivation and goes right into, this is the hardware that's available. Let's try to make it work. It's got sensing and planning that's going on. So the reason I'm kind of introducing some of this is now different ways of thinking about like this problem of there's an agent, it should be autonomous. And it's coming from a lot of different groups. And we'll try to synthesize all these together today. The part that will weave into this but gets complicated is what recently people are calling agentic systems. Uh, these are all examples of agentic systems. These are the original examples of agentic systems. And these days, that term is coming up because it'd be really nice to be able to have LLMs do more than not just, but basically be able to fetch information, but actually be able to do things around those systems. Okay. Does that make sense? I guess now there's even a third lens that's coming from the machine learning community, or at least the LLM community, that's like how to develop an interacting system that you can use a language model for. Okay. So, but the tricky part is to talk a little bit more about interfaces. So many of these different frameworks require some type of interface. So this one for robotics, literally talking about like the sensors and the actuators. Those are the interface between the agent and its actual world. In RL, it's a bit more vague. It's just sort of like actions and states. Although for anyone who's, like even working on your project, when you go to implement RL on some real hardware, that blob on the left becomes pretty ugly with lots of details, lots of motors, lots of sensors and cameras on it. And how all of those are used matter. Okay. So this is a bit of an understanding about how this interface can be changed. And really that the way the interface is designed determines a lot about what the agent or robot can do and what it can't do. All right, so let's be a little kind to my drawing skills for today. And let's pretend this is a humanoid robot. So now it's got like a particular design. It's got a hand with a couple of fingers on it. Looks something like that. Okay, but now like this is the interface for the robot. It's defined in its morphology. So the kind of concept I want to be able to introduce to you is, all right, so what if, let's say this is a hammer, okay, and it goes into the robot's hand. Has this changed the interface for the robot? Like basically, has its action space changed? Has its sensors changed? No? You seem pretty assertive and sure of that particular answer. Well, does that not happen to you in this case when you pick up a tool? Do you kind of still pay attention to your fingers in as much detail? Or do you start paying attention to the end point of the hammer for how it's used? Hmm. hmm Do you think, though, just as an example, could a machine learned model be able to learn that in this case, like the fingers don't matter as much? It'll activate like some other sub policy inside of a large transformer that now is like, this is the hammer swinging chunk of my understanding. Mhm. So you're saying a little bit that the maybe the not quite the planning space, a bit of the thought or task space may change depending on the tools that are available. Mhm. Okay, interesting concept. Yeah, other thoughts? Does that make total sense? Okay. The it's a bit of an interesting concept because it's nice to consider like the hammer change. Because like if you no longer have to pay attention to the fingers, it actually does make planning easier. Like the action dimension should go down. So then in that case, is it at least helpful to think about, okay, maybe the action space has changed. Hmm. Hmm. Does that come from an understanding of this change in interface? That's one way to describe it. But it makes sense that you still can't, there are two ends to a hammer as well. So I guess you'd have to think about whether or not you're swinging it to create stuff or swinging it to remove nails. But this, what becomes the notion of an interface often becomes kind of a fluid concept because it's a little about, these can cause also interesting changes in the environment, I guess. Yeah. Does anyone have some other ideas for examples of interfaces? Or at least something that you find that because you have that thing, it changes the way you interact or plan in your life. Yeah, a computer. Hmm. It is an interesting tool. Like in some ways, because of like the computer that does exist, it changes the way you plan, like the way you're going to think about problems, the way you're probably even going to do things. It's the reason why we're kind of like here figuring out how to somehow come up with algorithms basically that'll control stuff in the real world, partly because we're fixated on the concept of computers, algorithms, and those processes. So we're like used to that stuff. Hmm. Okay. One other, they can even be a bit more mundane than that too. Like using the metro, taking a bike. It's probably an interesting way where like all of a sudden, like you can define it at some level, a certain amount of your like entire dynamics function for your world changes once you're on a bike. Maybe you think about your toes as much or something like that, maybe not. But these interfaces have a very specific design. Like it makes it easier for people to go places on a bike. It also greatly limits a bunch of other actions. You probably can't swing a hammer nearly as easy when you're on a bike or be able to complete the same tasks. So these really like morph and reshape what I'll stick with this like human robot example for now. Trust me, this is a robot. In order to be able to think about this process. Yeah. Yeah, I suppose because it's in the car is in 2D. But then when you fly a plane that has the extra access of motivation, then you get to push up and down on the steering wheel. Hmm. Yeah, it's leading to a process where you should also think like even for yourselves or the agents that we end up making. So like what tools help them? So like having an interface for a car is even a good one because like I think the first car, I think it was just like a joystick like this, and then there's like an e-brake. But obviously we've gotten better at making the interfaces between like human beings and cars more or less better, so we can interact with them. But that interface helps a lot. In some ways today, yeah, we'll be talking about, all right, so how do we make an interface good enough to also make it easy for an agent to learn? At the end, we'll get down to some really weird stuff where we'll be like, okay, if we have a humanoid robot that's now making interfaces, everything this thing makes to help itself is also good for us. So that's an interesting concept. Okay, let's get down into some details for the moment, because now a lot of this is, so we want agents to work in the real world. What do we do? Because now there's like this actual interface or how to adjust it between the agent and its world. And I guess maybe one last step is a lot of these interfaces, they don't have to be physical. Like sometimes just like someone in here like writes a planning library that's faster as a new way to change, the design process that the agent uses to interact in the world. So in the real world, the idea is to be able to create agents that can autonomously collect data. This is where, for the most part, supervised learning agents, okay, they're not really agents. They basically ignore this process. Data just sort of like falls out of the sky, lands on your disk drive or, your solid state drive these days, and train over that in order to be able to get a model. It's interesting because, okay, but still the winning trend or ingredient these days is more and more data. So now if we can figure out how to do this autonomous part more, this means we can train agents to learn from their experience, but it's still this challenging process of basically figuring out, all right, some interface needs to be created such that it enables this learning from experience. Remember, if we had that humanoid robot and we just like applied the RL algorithms we've talked about so far in the class, the robot and all of its really expensive and very brittle joints would fall onto the ground and flop onto the ground the entire time, probably never explore anything interesting for quite some time. So I need to think about how to kind of operationalize the process of being able to automate and collect data at scale, and then also be able to do more interesting things in the world. Okay, so this is where this kind of problem comes in. So RL works great. It works really well in simulation, but it's not easy to always apply this in the real world. So this is often because there's a number of reasons. There's a couple of more like background fundamental theoretical ones where a significant number of the assumptions needed to train agents break before we even get to like the mechanical ones. So this is, when we're training agents, they often need to have full observations, use a bunch of on-policy data, and need to be able to sample like this function really well. This, be able to collect lots of trajectories. So this is, let's say we're going to start on this problem for agent needs to collect lots of trajectories mathematically. One of the first challenges of being able to do this is there's a few too many assumptions that are made here. One is, what if the agent can never return to the same state? If it can't return to the same state, it can't sample this distribution. This makes it really easy to like remove past mistakes, learn better, things like that. You can kind of say like, all right, I was having a great day or something like that, but the weather's a little bit gray outside. I accidentally fell onto my couch and I don't feel like getting up anymore. So the agent isn't going to learn anymore besides of that, beyond that state. These do exist in the real world in a couple of different ways. So this is where, if you think of this whole like screen, this little box here as basically the state space, there might be a couple of states over here that is, this one is, broke arm, something like that. So in that case, the agent can't recover from that unless, some other system comes in order to be able to repair that arm. And there's a lot of other of these particular examples, and they occur pretty often. There's even one pretty often example of this where, I don't know, if you're ever trying to collect data on a robot arm, one of the more annoying things that happens really quick is it's trying to move objects around. It accidentally knocks one of the objects out of reach. It can never reach that object again because it's a stationary arm. Can't move around. It can't do these things. Although I've seen a bunch of interesting papers that will then put like 4 other robot arms around that robot arm that like knock stuff back into the area that the one learning robot arm can actually use. But hopefully we can find some solutions that we'll talk about today where it doesn't cost 4 times as much as your original learning algorithm you're trying to develop. But this can also, one other way to do this is to think about trying to learn like partitioned versions of the state space. So if, broke arm is somewhere over here in the state space, just, have the agent not avoid this chunk of the world if possible, or have the agent visit this area of its, state space very infrequently or like as little as possible. It's the reason there are plenty of versions of these. This is kind of like stuff that is learned by human beings, hopefully as they're growing up over time. For example, okay, how many people in here have broken a bone before? One, two, one. All right. I think the rest of us need to get outside more often. Um, that's true is, but you kind of like you learn from those things, you kind of learn to avoid them. You might strain other stuff or break a lot of other things. But the process here that I want to start to talk about is not just about what was a common thing to worry about, like in the world when collecting autonomous data, as resets, which is basically in simulation, after the robot falls into the ground and would normally break itself, there's just like a button to basically turn back time. It's not something that's available in the real world. So there might be areas in here where the agent can learn from like a lower dimensional state. So break up the state space into areas that are more important to be able to learn to achieve some task. If we know, or the agent knows that the task is ideally somewhere over here for some optimal state, then it can avoid these other chunks, piece them back together in a couple of different ways. Okay, so the challenge with doing some of these, it's also connected to basically figuring out some of the limitations, is just do remember, as much as we're going to talk about a couple of algorithms, part of these are also to help with the assumptions for learning. So deep learning is supposed to be IID, well, needs to in order to be able to converge properly, which means that like everything in the data set is kind of determined randomly. But especially when we get down to doing stuff on real hardware, things become very non-Markov. So data is not independent. If you're training this data on a single robot, a lot of things related to that robot are embedded into the data, especially as the robot starts to degrade as it collects more data. So things are not IID. Also, things are not really identically distributed. So cameras will change a little bit over time. Lighting will change. Motor decay is a really common one if they don't break too soon. And IMUs are not really great at picking up like really good sensory information over time. Also, they can get knocked out of position pretty easily, especially after your robot falls on the ground. Okay, so to try and make things more IID, the process is to be able basically to have a method to, like, I don't know, if you're familiar with more stuff from D&D, like cast resurrection on the robot, bring it back to life how it was from before. And this is this process for whenever we do stuff in simulation, pushes the button, causes the robot to reset in time. And then the rest of this is pretty similar to how like RL just works. Collect some data, do some updates. The idea here is this step is what helps the agent at least not get stuck in a sync state forever. Okay, does that make sense? Avoiding these sync states will allow for a lot of autonomous data collection and learning. So the challenge here is, so not all these states are equally difficult. Most sync states have like a bit of a smooth curve that kind of leads into the sync state. So like if you're in a continuous environment, this is obviously the most like harsh version of talking about sync states. If you make one mistake on this particular rope, like the entire area around it is a sync state. So it's sort of like this. If this is the path, well, no, if this is the rope that the human or human robot would walk around, then all of the stuff, not in this state is essentially a sync state. Everyone agrees on that part, right? Like falling off rope, bad, really hard to recover from. I don't see any type of safety harness between that person's leg and the rope. In most cases where we probably want to use a robot, which we talked about already, which is like cleaning stuff, maybe doing surgery. I don't think we're going to get too many robots that end up doing tightrope walking, but who knows what kind of demos we'll see next year. But in many cases, there's usually a lot of states and then maybe a sync state. And there's really a type of kind of like inverse gradient around this state where like when getting towards that sync state, you can often detect that it starts to be a type of a sync state to get away from. You can think of even just naturally as soon as you start going up floors in a building to get to a higher level in the building, well, there's some chances that, once I'm up to the fourth floor or something like that, it could hurt basically being able to fall out of that height in that design. Okay. So this is where I gave that example where this happens really often, where a robot arm when collecting data will just like push the objects out of its way such that it'll never collect good data. And for those of you like working on projects right now and collecting some data, maybe this way to pre-train your policy, do check on this. Very often it's like using a random policy for a robot arm, just knocks all the interesting stuff out of the way and collects a whole bunch of not very interesting data. It's another reason why we want to avoid this. Okay, so one possible solution, because we all know that RL is fantastic, train a policy to basically learn how to rewind time. So from this, there's one policy that'll actually be the one learning the environment reward. Learn another policy that essentially tries to figure out going from any spot in the future, rewind time such that that robot will be back to that initial state distribution. And then we can just treat this, as a goal state that we'd want that agent to be able to get to, or even this distribution, like what we talked about for the Disco RL paper. Yeah, and that's just this idea where agent starts around here. This is sort of P of S0. It's going to wander out into many locations, and will be some other policy that'll basically rewind time. Call it rewind for now. It'll take that state, go back, undo all the states we made. Some of you might also know of these things called parents or guardians that tend to do this a lot for other people, mostly the young people as they're learning. It's a very similar concept here. Okay. So the idea is just to train another recovery policy. So here, this is theta R for the recovery policy in order to recover back to that state. It may not be too fantastic at this at the beginning of learning, but at the same time, the agent is not too fantastic at getting very far away from the initial state distribution at the beginning of learning either. So together, this doesn't make too challenging of an overall problem. So it's really kind of like break, let some other RL process handle going back for a little bit. It's its own RL process. And then the rest of this is normal reinforcement learning. So then here it's just, if you can determine this part, which we'll talk about in a bit, if it's in an unsafe area, then it's sort of like, okay, we'll stop. And then I'll figure out how to rewind time. Unsafe is sort of like estimating how close is it to one of those sig states. Okay, does that make sense? Any questions about what are not really called time reversal algorithms? But there's a bunch of work on basically reset free learning to enable RL to be used in the real world. Okay, great. All right, so then we're going to get into a variation on this that's going to be a little bit different. There's kind of two ways to think about this problem of collecting data in the real world. If any problem wants to be tackled, then like if you pick problems in general, they'll probably have some sync states. Often those are a bit more challenging to learn and a bit more difficult to deal with. But there can also be this like subgroup of tasks that don't really have sync states. And those might be like ideal to collect data on because of this lack of sync state. So this is, okay, maybe one way to get around some of these challenges, pick tasks where there aren't a ton of sync states, maybe even where there are none, and then just figure out how to operationalize those tasks such that an agent can learn very well. And there's been a couple of recent works on this that are what are called like scaling for deep RL or fully autonomous learning using RL. The idea behind these is there's basically a cost for this reset. And there normally is. Normally, if you've worked with some robot hardware from before, it would mean like the person physically going to that robot, repairing its arm, figuring out how to configure it, push the objects back into the reach of the robot arm. So let's say that we want to pick tasks where it should be always possible for the robot to take care of everything, because I've put on my extremely lazy professor hat where I never want to have to go visit the robot. It should totally take care of collecting all the data and operating by itself. So here, we'll talk about this work. Okay. So then here, let's get into this example. And when doing this, you can really take advantage of all the nice learning algorithms we've talked about from before and don't have to worry about making a reset state or a kind of reset policy. All right. That's upside down for you too. That's weird. Okay, so in this work, the idea is like, okay, how far can we take autonomous learning? Which is a person never really has to go visit this. It can collect all the data on its own. So it's sort of like you can think about that dishwasher example from before. You just kind of like push a button, come back later, things are clean. Now this is the push a button, come back later, the room is clean problem, is what this really is. Okay, hopefully if I start this, okay, magically right side up. Maybe we still need a few more LLMs to help us figure out how to code things better, but I'll get back to the challenges in PowerPoint in the future. So that's what this work is. It's got a couple of collaborators from earlier, and it's now figuring out, okay, can we make this robotic system such that we never really need to interact with it and to learn how to clean this room? And a lot of it is about figuring out how to really understand the weaknesses of reinforcement learning and machine learning, and then play to the strengths of it to pick the right task in order for like collecting data and training a model. So we've got this great robot on the right, which is the same one you can also use for the class, because we've got a couple of these. It's got a little mobile base, if anyone's familiar with like those vacuum robots. And then it has this WidowX robot arm that's also available for the class to do stuff. Okay, but all right, so in normal world, or at least in simulation, actions for this particular task are actually kind of complex. There's a lot of stuff going on. The base can rotate while the arm moves. It's not actually easy to figure out how to calculate the reward for this. So how does this agent get rewarded? And then here, there's sort of this odd initial state distribution. So if you want this to work, does it mean someone has to come in and like move the robot around every once in a while? In this case, the robot's picked pretty carefully. It's got a base, it doesn't have legs. It shouldn't fall over. It's not fast enough to fall over either, as far as I know. And we put some extra weights on it anyway to keep it have a low center of gravity. We could maybe think about using sim to real in this case, but most of those points on the top make it difficult. So this would mean making a realistic simulator. So even trying to figure out how to do a good job of simulating the contact physics for the wheels on the robot is going to be a challenge because rolling friction is not something that's easy to model. And the part that comes up a lot too is, okay, rewards often will use some privileged information in simulation. And if we need to do fine tuning in the real world, it's like, because maybe your apartment is slightly different than the one in the simulator, then it means we still have to go back and do all the work to be able to create this reward function. So we're not gaining a lot from using simulation here. Does that make sense? As much as simulation is fast, sometimes it might be not worth the effort to make a simulator if you can come up with a problem or a certain task that is actually much easier to do in the real world. Well, at least much easier to automate in the real world. So here, basically, this is going to be achieved by combining three things. So the actions are complex, all right? We're going to use a form of basically hierarchical RL here. There's going to be one policy that controls the robot arm, another policy that controls the base. However, they will both share the same reward function. They both only get a reward if the robot arm successfully grasps an object in the world. Here, the reward function is actually nice and simple. It's quite literally the robot arm goes down, closes its hand, brings its hand back up. And if it can't close its hand all the way, there's something in its hand. It's managed to grasp something. So it's a nice, you can just use like the encoders on the servo that are in the hand as the reward function. It's fairly accurate, although it tends to take a long time to find stuff. Resets were actually surprisingly easy to take care of. In this case, all we really needed to do after it grasps an object every once in a while, have it drive around randomly. Because it's not the process of actually needing a reset, like having to rewind time that's important for the robot. It just needs to add some diversity to the data, like kind of enforce that IID assumption a little bit more. So even if the robot just kind of like freezes its sensors and then wanders around the room randomly. That's enough to add now this separation of the data where it's not temporally correlated and collect data again. So we don't need to rewind time, which is good. It's really hard to go back in time. Okay, does that make sense so far? Okay, and there's just a couple of like design challenges still in some of the details. So one process here, and this is basically what the entire robot learning community is trying to do right now. Spend a little bit of time, like here, only the robot arm grasping part gets to grasp and collect data. The base is kind of like turned off. So it's focusing its time and just being able to practice grasping objects. So this is sort of like you can give the agent a little bit of this warm-up phase because we know it can be structured that way. Okay, so far, I don't know, the amount of human time that went into this is 5 seconds to turn off the base and just let it sit there and try and pick up this object. And then when it picked up the object, it would actually select kind of randomly where it should put it down. So it's just adding diversity to the data set that it'll learn to grasp over time. Okay, and then after this warm-up phase, all right, after it becomes good enough, it's kind of like bootstrapped its skill good enough, then the navigation can be activated as well. So now it both learns, like takes a grasp every once in a while after it navigates. And then from this, it can just run for a little while, be able to collect data. So it's kind of like after there's enough of this like base level learning, it already starts to get some good skill. Then it's easy enough for it to start to become like autonomous in its learning process here for being able to collect more data. It's kind of like, for people after, I guess high school is like the weird structure we've got in our society that after that, you're good to go off and like learn on yourself. You're good enough to add to society, something like that. What was interesting in this is, at least to save time in the process, is figuring out when to grasp, because grasping was really expensive. It might seem fast in this movie, which is sped up 5 times, because every grasp that the robot takes, I think it either took about 30 seconds to a minute just to like go through the operations of grabbing stuff, come back, and like sensing if the object is there. So avoiding as many of those as possible was helpful. And what we really did in this project is, okay, figure out some estimator for grasp success. So we can just like take an ensemble of like 3 networks that are figuring out how to do this grasp, see whether or not like what the max possible confidence is in that ensemble, make a grasp, if it's above some threshold. Otherwise, when the robot looks in front of it and doesn't see any objects, it'll just say 0 chance of success, keep navigating. Something like that. So it's learning here how to shape the exploration space, much like what we talked about in hierarchical RL. And then you can still do this navigation process. So it's basically the control for this agent is now drive around for a bit, check if there's basically something that it might be successful at grasping. If there's a chance, try to grasp. If there's a success, great. Drive around randomly, put that object down, and then drive around randomly again. If fail, go back to the beginning, drive around some more. Go in this cycle. Okay. Does that make sense? Good for some of the questions? All right. And this diagram works surprisingly well in this process. We're able to just train this particular agent. This is about in the middle of training. It only took about 25 hours to take this, put it in some room, starting from scratch. So this is no pre-trained model yet. So these days you can probably like warm start the grasping model with anything we've talked about in the class for Octo or whatever. The navigation would be different, although there are a few models for that, but you can still like reduce down this fine tuning process. But all the data collected in this project was used to train those models. So it's kind of this weird who is bootstrapping who process. But here, this will just work being able to start from scratch. Here's a couple of examples of it after training for a day. Yeah.
Does it navigate for like a set amount of time, or in the like grasp classifier like preemptively going, oh shoot, it's not.
The fixed amount of time, I think it was a quarter or a second is when it would run its navigation. And the navigation is basically like, it's 2 values, just like forward velocity and like angle of turn. that was a fun trick because then the mean for the network would be 0. So then the robot would drive straight in the beginning if it's initializing its random policy. Yeah, it mostly would only determine, it would stop after that quarter of a second, ask the grasp policy, any chance of being successful here? No, keep going. And keep doing that over and over with some random noise added to that. Mhm. And then this is the process after a day of training. So this is evaluation without any training. You could just put the robot down in the room. You know, it's not the fastest cleaning thing in the world. And I'm sure if you've seen even some of the humanoid robotics examples on the internet, they don't move really quick. They're all pretty slow for maybe a number of reasons. But this would take about 20 minutes or 10 minutes to clean up a room over time. And this is, again, basically learning completely from scratch. But the whole point here is to figure out how to automate this process. Because remember, at least we want to put on our lazy professor or research hat, where at least for the training process, like no one needs to come in and do anything to help this robot. It's learning how to add noise and variation to the items it has, such that eventually it would just learn all its own. Okay, I'll admit there's one exception to this where we had to go in and change the battery about every 6 hours. That one was, it never quite became a priority to do that because it was so easy. It took about 10 seconds to go in and swap. There's a little gray block right behind the arm. That's the battery for the robot. Start it back up again and keep going. Mostly because that would be faster, because recharging the battery took forever. So it was faster just to replace them really quickly. Okay. So then a little bit about joint training, which we talked about in the class from before. This is kind of a special example of doing hierarchical RL because they're both sharing the exact same reward function to motivate the exploration. So this graph is just showing that if the grasping policy is not continued to be trained while the navigation policy is learning, that's the performance it gets. But if the grasping policy is still like fine-tuned, continued to be trained along with the navigation, it becomes better at grasping objects, even in the stationary case. So basically at the end of learning, you could take the robot and then put it down back and it's like just sits there, doesn't do anything, but it's a better grasper even in that situation because it got to collect more data. Yeah. Hmm. Yeah. In this case, we started in the real world because there was a simulator that came along with this particular robot. It was not great. Also, the grasping physics between the end of the gripper and the objects in that simulator were also not fantastic. Because the research problem here is, like, if the question was, can you make a fully autonomous system? You might get a lot of contradictory information starting to start with your analysis and simulation to figure out what might work and what might not work. And in that case, when we did actually like do some experiments in simulation, because we just wanted to compare to like prior methods faster, it took a long time to do the kind of mundane things like figuring out how to find an object that'll fit in the hand well enough and still looks natural in simulation, which is not a research question. Like it tends to be like, well, now you're kind of overfitting the simulator a bit more than the real world. We did a bit of the opposite in this case. We picked these are balled up socks ordered off of the internet, but they're physically easy to grasp, but really, really hard to simulate. Surprisingly hard to simulate soft objects. They often penetrate the hands and the ground really easily. Does that make some sense? Mm-hmm. It's also, I mean, the way I put this is like, okay, what did I want to learn? Because I sure like at the end, a research paper for me like might come out of this. But in the meantime, I was just like, how do I program this up on ROS? How do I get these models to work? Where is the network going to live? Because it's not on the robot. It's actually in a different server in the corner of the room and figuring out how to automate that process. So I wanted to figure out, okay, if I wanted to make that system, what are all those things? And didn't learn as much about simulation. So it's kind of learned the ugly bits of trying to get it actually working. Okay. And then the nice part about this too, works in other rooms, even if there's a bunch of weird lighting changes, things like that. And in here, there's different objects. These are kids' toys that are like little stuffed animals, but they also fit inside of the gripper. But here again, it was just like put the robot down in any of these rooms, let it train for a day, and then at the end, it has learned a policy that'll clean up that room. I'm sure if you did this across more rooms, it would start to generalize across rooms as well. But here, we're mostly focusing on what you might want to think of as like infinite shot generalization, which is just like RL works from scratch. And it does. Zero shot generalization, less easy to determine. And then here we compared this a lot to, I find that like the random navigation and the random everything are not a good comparison, but we also spent about 3 to 4 weeks trying to create a scripted policy that would like detect an object as a blob on the screen, point like the robot more towards that blob and go grasp it. And it would work pretty well, actually, but it doesn't scale super well. So it would work, but it doesn't end up being the most efficient. So if we took our system, just let it train long enough, it'll always end up doing better than like that expert scripted behavior. You've got to get all the parameters right. The blob detector doesn't always work. It doesn't always pick like the most, like the best blob that might be in the screen, things like that. So if you automate the system, it can learn all the corner cases and stuff for it to eventually be able to do this faster, more robustly, things like that. Okay. Does that make sense? Hmm. Yeah. And this was kind of a combination of, this was a great robot to pick for this particular problem. This is not something I would do with a humanoid robot. It will break really quickly the first time it falls. So here, this is like, think about the problem that you're going to solve. Do you really need a humanoid robot? Do you really just need to be able to figure out how to automate a system? The battery life for this was fantastic. From the humanoid robots that you can purchase, which is about two of them, the battery life is about an hour, and it takes a while to recharge that battery. Okay. And then, yeah, there's definitely going to be some extended work off of this into the future where this is nice and self-contained, which is one of the things that we really wanted to focus in on this project. So like there's no other sensors needed. Technically, all of the learning can be done entirely on the robot. The reward function is on there. So you don't need anything outside of this. You don't need to add a motion capture system to detect the rewards, nothing like that. It trains with extremely little supervision besides being able to do change the batteries. But the future work is still beyond this. Like we wanted to take care of all the other repetitive tasks of cleaning over and over. The part that was definitely more interesting is, okay, what do we do next for the environment? These environments are kind of simple in some ways here, like a room with a couple of socks on the ground, not a lot of diversity in objects. It's a kind of an office space. And it was actually good. Small anecdote. This was during COVID. So one of the reasons we're even able to do this paper, like you're asking, do your research during a pandemic. There's a lot more office space that you can use to run your experiments. Kind of a joke. Try and get some space to run stuff. Unfortunately, that or like do experiments late at night when people aren't around. But having sort of more various environments is very helpful. And still thinking about what the agent should learn. Here, the reward function is just grasping. So eventually this thing will like collect everything in the world. That's probably not what we want, like the best agent to do in the future. Okay. Uh, any other questions about the project? Good. Yeah.
So what were the differences?
Not quite. So like the action space was actually discrete. You can kind of think of in front of the robot, there's a little like grid on there, like cut out in lasers, and then it would pick from that grid. So it was a discrete space for grasping locations in front of the robot. Yeah, a 2D plane, basically like mapped down onto the floor, and then it would grasp from those locations.
So it's like one shot, like you set a command to grasp or like one shot approach.
Yeah.
Like
Yeah, so it wouldn't. automatically figure out how to try and retry again. So there was basically a inverse kinematics controller that we designed in ROS just to take like, here's a position in front of the robot and then go and like complete a grasp motion at that position over time.
Sure.
Yeah. So that also helps save a bit of time. Again, but that's the point, is that that's why I tried to like lead into this about the interface that was created. So we did create like this inverse kinematics interface to make the control problem of actuating and picking up objects okay and a bit easier. I know these days we'll probably collect like a couple of million trajectories and try to train the biggest language model that we could possibly fit into our GPU to replicate that process, which we coded up in IK in like half a day on the actual robot. But it also depends, I guess, a little bit on like, what are you trying to show in the project? This project was, we want this thing to learn autonomously. And most of the work was just that IK controller took half a day. And there was some tuning. Mostly we did a lot of waiting for this thing to go in many rooms and clean stuff. Probably like 2 months of experiments, just sticking it in a room and letting it collect data for a while. Also, these robots are cheap. So that was not one robot. I think we had 4. So they could all collect data at the same time for scaling. That's kind of like why it was helpful doing this during COVID, is now like most of the meeting rooms are empty. We could use those for collecting data. Okay. Yeah.
The model is slowly wearing out. Like, how do you know the control? You have to give it more torque or more input to the model. Like, slowly the policy will work different.
So what would it need more torque for? Like for driving? Hmm. So I actually haven't seen any research, well, at least in the robot learning community, that does try to account for that, like the degradation of hardware and how to adjust its control policy. I mean, it will definitely kind of exist inside some of the data sets that we've created, but most of them, when it starts to wear out, it starts to not work as well. And then we kind of put that robot aside. But it's not the ideal way to go about things. And the robot arm here is a servo, so it doesn't really have torque control that it can like increase or decrease. So you need a nice robot to even be able to do that. For anything cheap, it just breaks, and then you replace like that whole motor at the joint most of the time.
It obviously breaks.
Kind of, yeah. But I guess people also change their interface a little bit too. Like they grow over time. You can like increase or decrease muscle mass and other things. So we do our own kind of adjusting. We figure out how to get around it. But robots are pretty easy many of them are easy to repair. Yeah, but nothing quite like that. That is a good question. And if we're gonna like keep robots working for a while, it's actually one of the things I think about a little bit more when it comes to all the humanoid robots that are being developed. How long are they going to last? We'll see how that works out, because usually there's very strict like rules in industry settings for like, this is a robot arm that's guaranteed to last for 50,000 hours of operation. And you're buying that as well, not just the hardware, that guarantee on operation time. Yeah. Okay.
You mentioned you have like multiple robots running at the same time. Did you guys detail like because I'm interested in like, any evolutionary kind of stuff, some robots trying to policies in a better one ways.
Not quite. So the robots operating at the same time was to collect data. They weren't sharing data yet. So that would be a nice version, maybe for this project next, for like scaling up data. But you can maybe go look at the paper, Deep Reinforcement Learning at Scale, where like Google kind of did a version of this, and then they're learning to like sort garbage and garbage cans across the building. And there I do think they had more than one robot operating at the same time, doing the same task. Yeah, here actually, when we would train like the painful stuff of robotics, like one grasping policy at one robot did not transfer to another robot, like not without any more data. Even we felt that a lot when we were doing the making that scripted policy. That 3 weeks that we spent doing that, so 95% of that time was just calibrating the grasping policy accuracy so that it would line up with the grid. The rest of it was like the blob detector and stuff took like half a day to put together. It was just calibration is a tricky problem when it comes to robotics. It seems like an obvious one that machine learning could solve, but hasn't been an as much interest, kind of. In some ways, the large foundation models that we use that do state stacking and then action binning kind of can do calibration in there to detect, okay, like it saw these last couple states after executing this many actions. Okay, so actually in this, we can figure out that the friction in this joint is a little bit off compared to normal, but it's not done explicitly. But yeah, future would be collecting a nice large group of robots and using data across them. Okay, yeah. Other questions? Okay, all right, good. Let's take a break. We're already a bit into it. I will come back at 2:49.
Folder creation.
The Slack message?
Yes.
So did you send an email with me in the IT group so that I can like just okay that email?
Like, yeah, I think for the first email I sent to the IT team, I also included you. So
Okay.
you answered to the like for
Is that not enough of a confirmation for them?
I don't know. Like there's a full I sent you the message in the it asks like some kind of confirmation, but I don't know what
Yeah, last time I just like screen grabbed the email really quick and like signed that on my tablet and sent it back. And that was, yeah, sure.
maybe the first email I also sees
If that's good enough for them. I guess I thought,
I don't know. It's just a form. I think they just want something. If it's not enough, I can enable ask something.
oh, so this is because you'll submit like a Google form and you need to like upload an image or something. Okay, yeah, I'll do that after the class because I'm currently recording my screen. Yeah, sure. Uh, all right, everybody, let's get started again. All right, so we've talked about this a little bit in the class, at least, using large models are nice because they can generalize well. They're also very slow. And like, even if we just wanted to use them for inference on some robot, so at least I'm not, maybe I shouldn't pick on anyone in particular, but basically most of the models are running at like 4 hertz, something like that. There's definitely a couple of other challenges where if you wanted them to learn in the real world, they'd need rewards. But this is a bit of a challenge. But There's also some notions coming up lately with a few people are probably familiar with these, where is it possible then, so if this is always this fixed amount, what about trying to think of more adaptive compute here? So you probably, at least some of you are familiar with a lot of the work on like reasoning systems lately. And then like the amount of time or the amount of tokens these days that can be used can actually change. So there's sort of like an amount of reasoning time or tokens or whatever that can be spent to compute an answer. So this might ask the question is, you might think about this too, because this is a notion, especially for like learning agents. You can think of like, so like how much reasoning time do you think is necessary, like that you use when walking, at least at this age, versus, like the amount of reasoning time that probably goes into planning your current project for the class. You probably spend a little bit more time working on one of these versus one of the other ones, right? One of them probably takes a fraction of a second. The other one might take a month or two, at least scattered across some time over those months. Okay, so actually, how can this kind of process, or at least concept, be even applied directly to RL? Because there's this problem that we haven't really talked about much, and it's not really talked about much, at least in the RL community. It's much more on the minds of the robotics community. One short way of saying this is, okay, actually, the world does not stop while the agent is computing its action. Like from the state to when the action comes out, a lot can change. Even in a quarter of a second, a lot of car accidents happen in like less than half of a second. So there's no time to react. So then just like thinking about this process is, okay, should RL algorithms fundamentally change the way that they're being constructed, at least in their objectives, such that they can maybe take advantage and they're penalized by how much time they need to take in order to actually compute an answer at a specific state. So there is a bit of work already in doing some area in what's called real-time reinforcement learning. This is a more common thing in robotics, and I really should add some more references for just doing like real-time planning, which is kind of related to this in some ways. But the point of some of this work, and it's some of the work that I've been doing with Matt, Matthew, and Gopesh here at Mila, but basically coming out, okay, how should algorithms be designed under the constraints that they actually need to do stuff in real time? If you're only given 10 hours to complete a task, or like a robot is to learn and complete it, what is the best way to be able to do that the fastest way possible? And basically get the best regret. And then how to design those algorithms. So here, this is going to get maybe a bit more odd, so feel free to like definitely chime in for questions. But this is like normal, like the sequential learning paradigm that we've talked about in the class. There's a world, you query the world for some state. To be honest, it takes some amount of time to be able to sense the state of the environment. There's going to be some learning step. So somewhere there'll be like a gradient update or a policy update. And that'll update some parameters. There'll be some inference step, which will then like forward past that new current state through the actual model. And then an action is actually made. So there's actually like 3 different things here that can all incur a different amount of computational time and cost before the agent can even react to what's going on in the world. Okay, does that make sense? And then how we can change this a little bit is, so first step, what if we started to think about this in a asynchronous way? So a lot of these pieces don't always need to be done at exactly all the same time and in lockstep. So here, there could be a number of different learning threads. So this like tau of L here is basically like time it takes to do like just a gradient update on your model. A lot of those can be running asynchronously, like asynchronously at the same time, going over data. There's definitely a few algorithms that do that. There's going to be some tau of pi here, even though it's a bit blurry. And that's basically the time it takes to do forward inference in the environment. And the last part down here, so this is like tau of M, like the model, like how long does it actually take to like execute that particular action in the world? And then like the regret of actually being able to achieve the highest amount of reward in the lowest amount of time is this can be the sum of all these together. But now at least this one has been kind of like split off, where now it's mostly state inference the next state. So at least we can reduce the learning costs when it comes to regret for the agent. But we may actually also, in some ways, want to be able to do that adaptive compute. It's a bit harder and there's really not too many algorithms for it. But at this stage, like if the agent is just walking, it can probably do a faster inference step because it doesn't have to do a lot of reasoning at that stage. If it's having to figure out how to construct its project for the class, it's going to probably do a lot more inference time here. More time is going to go by in the real world as that's being computed, but it should hopefully be able to take a better action in the future. Okay. Any questions or thoughts? It's totally clear. Okay. Maybe I'll give like an example too about some of the bonuses here. So like in sequential learning, this ends up having like the cost is basically the construction of all those 3 different objects together. But now let's look at this basically on a clock in order to understand what's going on here more. All right, so if this is on the top, this purple line, let's just say that's like the limit of the sensors that can actually be used inside of the environment. So literally your hardware can't operate any faster than that. And the sequential inference like paradigm, it would mean that, okay, the red line is basically like the learning chunk. So the maximum basically that now combining the learning and inference process, now it has to skip about 10 steps before it can actually ever make an action. And its regret, like what it can actually do in the world is bounded now. It can't be any better than that. So if there are things that happen in between those 10 steps, it's going to get less reward at the end of those steps because it just literally can't computationally react to it. Does that make sense? There's just always going to be some cost and delay while it's computing stuff. And then the difference here is now you can have 2 versions. We can now asynchronize the inference process and the learning process and kind of insert them in here at different points where they're not going to be delayed on top of each other. So at least a lot of the bound here becomes, it's still technically 2 things because this, we'll get to one of the details on the next slide because it's not just about the inference time that we're trying to reduce. We still need the agent to actually learn such that that policy becomes better. So it's still the amount of learning time that it'll take, like wall clock time in terms of like picking up new stuff from the world, learning how to do better with that information, and then transferring those parameters to like the inference policy. But then that collective kind of ugly paired soup is overall what we want to actually be able to optimize. There's more so like what people do as we have to like make choices about what we spend time on, and we kind of have a fundamental reaction speed too. Like no real person can go faster than like 10 hertz. Is like the time it takes about 100 milliseconds from signals to go from your hand to your brain. So that round trip time is limited. You can't really react faster than 10 hertz. Okay, does that make more sense? What we're trying to reduce here? Okay, then you end up getting these costs, which are defined a bit more here in detail. Remember, this is basically like a function of time. So there's going to be a learning cost. There's still this inaction cost is what we call it here, but that's like the time it takes to actually be able to compute an action. And then there's some delay in the environment, which depends on a couple of other things, but let's just say that's kind of fixed or this gets really, really ugly to describe. Okay. Still following along so far? Yeah, so if you really, so good for following along. This is actually a pretty dense piece of work and understanding it. So if you want to go dig into the paper, you're more than welcome to. But then basically how we can apply this is now let's take some sort of environment that actually has like a real-time, problem we want to solve. It's not quite a reaction speed, but it's also a learning one. So somehow we managed to predict the future. Pokemon seems to be a really popular environment for people to experiment with this year. And then here, what we're doing is comparing to different like learning setups for algorithms. So there's still the sequential learning paradigm. So this is basically just like running DQN on the bottom sequentially, like exactly what you did for homework 3. The difference is the line on the top has now got extra threads in the background that are iterating over the data. So those don't block when actually making actions. And it can do a little bit of like adaptive learning and actually being able to compute part of the action. And now this is wall clock time. So this isn't like, like number of time steps or samples in the world. This is like, how long did it take to train? We fixed the hardware that was used in order for learning, so that hopefully it was like more or less trying to be fair here, because this actually gets really complicated because now performance depends on the hardware you use. And now you can run a bunch of experiments over this and see that like being able to do this asynchronous learning where it's separated, and now the regret that ends up being learned here is much better for this algorithm that can do asynchronous staggered learning and training updates. In the future, if we want to apply stuff on robotics where we can say we care more about like samples, but what we really mean is time overall. Like even if you talk about samples, you'll have to like reset your robot and go back and collect more data. So it's actually time running on that robot. And trust me, the battery on the robot speaks in time. It doesn't really care about samples. It trains according to its like use at that time. Okay, questions? Everyone really likes real-time reinforcement learning now and planning and kind of gets the concept at least. This will most likely, because one of the reasons we're doing this, and now like the next step for this project is, so now we can use like an LLM for the policy, and we can use adaptive computation on that policy as well, training it asynchronously, because for some problems it doesn't need a lot of tokens to make an answer. It can be really fast, up to like 100 hertz, because it can skip potentially like a large chunk of the network and actual processing. For other questions, it can be way more complicated. Need to do a lot more reasoning. Maybe it needs to call, deep research or whatever is needed these days to process a bunch of stuff on the internet before it can make a decision. Okay, but this, especially as we're working on applying these models to real hardware, these types of like formalisms and ways to think about how to actually optimize the problem will become more important. Especially as a lot of the robotics companies are using large models, are concerned about the amount of money they're spending on compute in order to make their solutions actually economical and not just flashy. All right. All right. So then beyond this, so this is kind of like the area so far we've talked about trying to be able to automate things and then try to get things to learn in a reasonable amount of time. For a bit, let's cover some stuff related to safe reinforcement learning. So now there's this, okay, well, hopefully we can make stuff pretty autonomous. Then we can also make them learn in real time. And we still, the agents, don't want those to actually break themselves in some way. So a little bit about this actually looks at the problem slightly differently than what we've talked about in the class, but it's got a lot of similarities to still like maximizing rewards. But now there's a constraint function. So like do as well as you can in order to collect rewards without getting like any possible constraints that are actually activated, because those will end up reducing the amount of rewards, or basically the sum of these two that are achieved. Okay, nothing too complicated there. The complicated bit here is really the pretty large space of kind of safe learning models that have been used. There's basically on the left a lot of model-driven stuff. So if you're looking into doing some safe learning, which at some point these companies have to do this or they're never going to get approved to be able to put in someone's house. You can start out with a model-based way of doing this, which work really well. They're like mathematically fantastic. The challenge is being able to come up with the model. Like what is going to be a good enough model to know that it won't actually go into some sort of unsafe area of the world. There's some data-driven approaches that I'll talk about a few of them next, where it's basically maybe you can learn that model from some data and then be able to learn from that. There's also a couple of like risk-averse methods that try to estimate that cost function, model-free, and then be able to balance those. And then there's basically everything between these two ends of trying to combine algorithms. If you want to know a lot more about the details of the like many type of safe algorithms that are being used in this case, because maybe you've got a really safety critical application that you're using for your hardware, go have a look at this survey and you can dig into some of the details. We're going to pick one or two real kind of quick here and talk about kind of their connections and what to think about how to use these. Because one way to sort of think about this, and we'll go through two steps, is if we're doing a data-driven approach, how much of the safety can we kind of put into a large model? Like if that large model has some concept already of, robots should not jump into a pit of lava, that kind of common sense could be very useful for being able to get around safety. And then, our language model can be used for this chunk of computing the cost. Because a lot of the challenge doing safe RL is that cost function. How is it estimated? How is it computed? What form does it take? Because it's usually not known for a lot of problems, or you need some really good engineer to describe it beforehand. And let's just say they don't always make perfect models either. So it's kind of, hopefully it's correct. Okay, so one of these is basically more of the model-free version of this. If the idea is to be able to minimize an objective for some reward function, this is like reward for the actual task. One idea, create basically an extra Q function. Think of it as a critic. In this case, it's called a safety critic. And the idea is basically train this Q function on some other really safe task. You can even look at the autonomous task that was in, like I was just showing before the break, like use that to collect all the safe data moving around in the environment. It definitely scratched the walls quite a bit as I was collecting data, but it didn't really break anything. So it's kind of like this totally safe environment to figure out some common sense, and then use this to basically weight the way the actions are going to be selected for the agent. So if it doesn't know much about what to do, use stuff depending on what seems safe in the prior environment. Otherwise, as it starts to learn, it might start to explore some actions outside of the actual safe area for the previous model. And then it can kind of build on this. But this concept here is just think of this for the moment. It's like, great, there's some model that we can use to define safety. And this could be quite a good advantage for what we've got going on. And then in this, you can design an RL algorithm that uses this, where, okay, the idea is still to, train this pre-designed policy, and then basically select an action from the policy that's learning, as long as the Q function that's actually learning right now doesn't end up going too far above this threshold. Right, so select an action for Q safe that is less than epsilon. Yes, so this is fine. This basically says that like things are still a good value there. And then do still some update on the original policy that's learning, such that it gets to learn from a combination of these two Q functions that depends on that epsilon. So it's kind of, things are going to be safe according to that critic. If things are maybe really unsafe, you can select from the prior policy and not the new learning policy. Okay. And this is using some of the data collected from that safety environment. Okay, does that make sense? There's a couple of different ways to like use this model for what's going to be described as safety. This is pretty strictly in like the RL paradigm here, where it can be used to select or not select actions. And then in the end, where the idea here is still to get good rewards, and after some fine tuning, but the idea is to basically still be able to get the same performance with far fewer falls or some sort of like crashes. It's actually kind of connected back to resets that we talked about before, because usually the agent is kind of like a reset whenever it gets into a bad state. And in this case, the version that is using safety critic RL here, the blue line, ends up getting much better performance in many cases than just that original critic, like basically without any safety considerations or other prior methods. Okay, does that make sense? Basically kind of do what we normally do, and then you can weight the Q function and selection process according to that Q function that says in a normal everyday time or task, this would still be a safe action to take. Okay. But so this is sort of a different concept, but so like safety can be very relevant, but we also talked about sync states just as an example, because that's basically like, Those are the states that you really want to avoid when you're thinking about training an agent that'll be able to avoid some safety. But in many cases, it's sort of like, how important is it to be able to recover from those safe states? Because we don't really have an option in order to be able to go back in time. There's definitely us, or like humans and biological systems, as an example, that doesn't need to go back to any particular state. It seems that we can learn without having to avoid entirely sync states. And part of the reason for this is, well, there's actually a lot of interesting conditions in the environment that biological systems exist in that kind of already take care of some of the assumptions that we're designing these algorithms for. So, for example, there's all types of noise in our environment that naturally add diversity. They help avoid a lot of these sync states. So then maybe figuring out how to recover from those resets isn't as important. Maybe instead, the environments that we're training agents in should just have some fundamental noise always added to them, and that diversity is good enough for it to be able to learn. So this is kind of another version of like, should this be an algorithmic problem, or actually is the environment that we're trying to train our algorithms in actually a good representation of what they're going to have to deal with in the real world? And there's some other versions of this. It's possible to always escape some sync state. A simple way of doing this is just adding some random noise to like forward dynamics such that things aren't perfect. So then you kind of avoid some sync states. And this even counts for if there was a sync state that exists in here, kind of like poof, the agent gets out of it because of this noise, which can happen. And you can even shape some of the environment. So at least until the agent learns how to avoid them, can kind of like start in some state space. Just as like we're kind of limited in terms of how far and how fast we can go. So you can begin in the kind of experiment and environment as some sort of subset of the state space and then expand that over time, rather than having to worry about making a specific algorithm for this process. So at least in this paper, we can show that instead of creating a whole new algorithm or two in order to solve sync states, if you just add noise basically to the original dynamics for the problem, the agent will still learn how to deal and avoid sync states in the future. So it's kind of like a short message. If we're going to be working on algorithms, let's make sure they're going to be algorithms that are actually helpful and will work in the real world, and they don't kind of just compensate for stuff we inserted into a simulator that's not really a part of the real world. So I've got to be careful about that stuff. Okay, does that make sense? Maybe I spend too much time thinking about this, but I just want to make sure we make algorithms for real problems. All right, so we've got a bit more time, so let's cover a few more details. One of them is kind of going another step, which is understanding what level of interaction is needed. Is often, simulation, and we can say that like even simulated tasks are too simple. But we need to make sure we're not kind of making that kind of like vacuous argument, because there's a lot of real world tasks that look a lot like simulation. So here we want to say, great, we've got an experiment in our paper, it's on real hardware, but really we almost like design that particular task such that it looks like the simulator. It's a bit of a problem. I mean, for some reasons, because it works in the simulator and we want to get it to work in our experiment in the paper, it's like, let's not make it too different than the simulator because we know that's where algorithms work. But it kind of asks sort of at least one of these questions, like, is a stationary arm that's like stuck on a table where if it knocks things away from itself, it can't reach them anymore. Is that really a real world experiment? Does that agent get to navigate around in the actual world? Does it get to explore all the possible diversity that would come from existing in a world like this with other agents and things that change? Certainly not strongly. So in that case, I don't know, if you want to make a stronger claim that you're doing real world experiments in a paper, maybe add some more diversity to that, let some noise creep into the actual experimental process. And this is where there's also, because there's just generally not a lot of diversity in simulation or even a lot of the real world experiments that are done. So hopefully we keep pushing on this some more. And even we've talked about in this class where, okay, the agent can pick up objects and move them, but it's not a really hard task, not a lot of lighting diversity. Let's at least kind of keep pushing the boundary in what we keep importing more and more real stuff into these experiments, make it seem more like the wild where they will exist. So like not in warehouses. This is like one of the reasons why self-driving cars are really difficult to do because they interact actually out with other people in the world that changes all the time, not in closed rooms with like one light in the background for some reason, and only a single window. Okay. And all right, a little bit of this is also connected to like agents, and there's even some biological experiments to show they need to be able to interact with the world, even in order to be able to develop the proper perception abilities that exist in the world in biological agents. So for example, so there was this experiment from a while ago that I'm pretty sure would be illegal in order to be able to do these days. But what happened is there were two cats, really two kittens. One was put in a box where it can't move its arms and legs, so it's only receiving passive information. Well, the other cat gets to walk around in a circle, so it basically does get to control where it goes. So it's sort of like actively collecting data during its life. And it turns out that the cat that was put in the box that wasn't able to move its legs was basically never able to develop properly any of its like perception systems or its motor control. I think for the rest of its life, but I don't know the details for the rest of the experiment. Like this process of not just seeing stuff and not just like interacting without seeing stuff, there needs to be this loop of like collecting stuff, and that stuff that is collected comes from like the agency of the actual agent, such that it aligns well. But this also means, so if we just have stationary robot arms that can like only do so much, they're only really going to learn so many concepts about the world, especially if we're the ones only collecting data for them over a couple of points, they can't really expand on that skill much. Instead, if you're more into playing video games, I at least borrowed this, like the task should be much more on this other spectrum of like real world, very open, lots of diversity, other agents. That'll really be like the foundation and frontier of where agents should be going in order to be able to learn a lot of stuff and eventually interact in our world. Otherwise, they're going to be stuck to working in very carefully designed and instrumented warehouses for a long time. Okay, does that make sense? This is my story on like the importance of leaving the warehouse, or what I'll even call the lab space. Even if it's in the real world, if it's still inside of a carefully designed warehouse or lab, it's still not really achieving this flexible learning, strong learning agent system. Okay, good. Everyone wants robots in the real world now, stuff outside of the lab. Okay. That way they can help with more things. All right. So, all right, let's stop there for now. We're already at 3:20. And then I guess we'll pick right up into agentic learning when we get together on Friday. And do remember, because I totally forgot, Friday we're back here. Turns out there's like 6 different parties happening on Meal on Friday, and there's going to be no free rooms at all. So I guess you'll be here learning about the best party, which is about robot learning. So we'll be here. And then maybe 2 other quick notes, which I'll share on Discord as well. So Friday we're here, Wednesday we're here. But that's kind of like the last-ish class, and we're going to kind of do a field trip at the end of that class. We're going to go look at the hardware for the lab. We're going to go do a couple of demos and stuff, and people can start asking questions about how to work with some of the stuff for their projects. That'll be like the second half of the class. And then the Friday after that is we've got our last guest lecture, which will be the last Friday. And then, so I was able to line up one other guest lecture. They were only available April 25th. So you're welcome to join the lecture, and I'll put that one online, and it'll be from Claire Lyle will give a talk on like scaling deep RL algorithms on April 25th. I'll put all this schedule on Discord as well. But just make sure you show up here on Friday. Me as well, because I almost forgot last time. All right, take care, everybody. Mm-hmm.